So the word flux comes from the Latin fluxus, meaning flow, and we're going to talk about the idea of electric flux. It does not mean electrons moving from one place to another, but it represents the idea of electric field going through an area. So it's a flowing of electric field more than it is a flowing of electric charge. And I've got this machine that I've made. It's a few years old, so it's kind of dirty, but I call it my flux catcher. And it is a loop made of metal. Here you can see that it is a fairly continuous loop, and the idea is that if I point it in the right direction, it can catch flux going through it. I'd like you to think of it as if, in this sense, when we get to magnetism, it will be a little bit different, but in this sense, I want you to think of it as a screen that I could wrap around. I could have it flat, or I could wrap it around and form a closed sphere out of this screen flux catcher. So if you have a faucet, let's put a faucet here, we'll put a handle on it and say that out of this faucet is coming some water. And if water is coming out of the faucet, then you could put your flux catcher right here in this stream of water, and if you oriented it so it was like flat like this, by this I mean it's like this direction, like this, then you would catch a lot of flux coming out. In fact, you could even wrap it around the faucet and say that there was flux, positive flux, coming out of the flux catcher. You could wrap it around and make a solid surface. Let's see if I can imagine this. Can you imagine wrapping a mesh bag around the faucet and find that there would be net flux leaving from that faucet? Okay? And you could also say, there's a drain at the bottom of this thing, right? There's a sink here, and help, color for sink. So if the sink is like that and there's a little hole in the sink here through which water is exiting, you could put a flux catcher around this hole, make a dome of the flux catcher, and you would find that there's a net exit of water through, or into, I guess kind of into this flux catcher right here. So it's about something going through a surface. And Gauss, oh man, Newton would heartily endorse Gauss to teach you about these mathematical concepts. Gauss was a fantastic mathematician and physicist, and well, let's set up some electric fields. You could make electric fields that point in a direction. Like you could make a steady electric field like this. How would you want to make this? You guys have an idea to make an electric field that points just to the right?
You have two pieces of metal with different charges.
That's a good idea, because if I have just one charge, I get a diverging electric field. But this electric field is uniform somehow. So I probably have a bunch of electric charges. And I'm going to have to say, well, let's figure out which side is which. One of these sides is going to have to be positive and the other one's negative, right? Which one's positive? How did I get the electric field pointing to my right?
Would it be, I guess it'd be on my, so your left would be positive?
My left is definitely positive, and we're using red to represent that. So I get a sheet of metal and I make it positive. And this sheet of metal, if I want the electric fields to terminate here, I'm going to have a bunch of negative charges over on that side. So then I've made an electric field that points uniformly to the right. If I put the flux catcher down like that, am I going to catch any flux?
No.
No. In fact, what I find is that the electric field is not going through the flux catcher at all. But if I rotate my flux catcher like this, then I get maximum flux going through it. So there's some kind of an angle that represents, it's a sine or a cosine. Let's be careful with it though, because you said this was parallel, but I don't want to call this parallel. There's something that I want to point out about my flux catcher. This is the area vector of my flux catcher, and it points normal to the surface of the flux catcher. So the area of the sucker is out, and I'm going to argue, I'm going to try to use this consistently throughout the year, that this is the direction in which the flux catcher is parallel to the electric field. So the flux catcher catches maximum flux here, and the flux catcher catches no flux right here. So flux is going to be represented by the capital Greek letter phi, and we'll say that it is electric field times area, but we have to figure out whether we want a dot product or a cross product. Are we thinking there's a sine here or a cosine? We do want a cosine because we want the area, which is to the right now, to be parallel to the electric field, which is to the right now. And so we have a dot product. This is electric field times area times cosine of the angle between electric field and area, where area has to be defined as out of a surface. So if I have, again, we were talking about closed surfaces, things that loop in on themselves, like spherical flux catchers. And in that circumstance, the area direction for these suckers is always out. That is a strange concept, but it's one we've been working with for a little bit, and I hope you guys are okay with that. The area points out for a bag like that, for instance. All right, so let's use this concept right here, and let's also establish, now this is Gauss's law. Gauss's law is a fantastic statement. This is electric flux, just a definition. It is electric field dotted into area. And Gauss's law, Carl Friedrich Gauss, says electric field dot area is flux, sure, but guess what, guys? It's also, well, it's the charge that you've got inside the flux catcher divided by a constant of the universe. Whoa, that's pretty simple. Let's call this the charge enclosed. And this is epsilon naught. It's the permittivity of free space. Boy, that's a long one. You can call it epsilon naught if you want. And epsilon naught has this cool property. Epsilon naught is defined to be 1/4 pi times Coulomb's constant, which makes a lot of sense in electricity, right? Yes, it does. Yes. So this is just another way of defining this, and I want to do some examples of Gauss's law. Now, this is how our book presents it. I mean, the book doesn't even have the dot product, but you know that we want to study a little bit of calculus on the way. So we're going to say that flux is actually the integral of electric field, but we have to dot it into a differential area, and we have to have an enclosed surface. We have to be going over some area, the surface area of our Gaussian surface. So we create a Gaussian surface in our minds, Sam. This is not something we're making, but we're going to say in our minds we can find, well, Gauss's law is incredibly powerful because we're going to be able to find the electric field from Gauss's law. We'll be able to measure the charge that's enclosed, and we can find the electric field of anything based on this really, really powerful mathematical tool. So let us get ourselves a charge. And here it is. We'll call it Q1. And we're going to make a Gaussian surface. And Gaussian surfaces are always made so that their symmetry makes the integral fantastically simple. In this case, do you know which way the electric field is pointing around this charge? Well, unless it's a negative charge, and just to spite you, that's what I'm going to make it. It is in everywhere. Very good. Or very wrong. So the electric field is always pointing in here. And that implies that we should make a certain shape of Gaussian surface. What do you suggest?
Circle or sphere.
A sphere, yeah. It's actually got to be a three-dimensional surface. So we're going to make a spherical Gaussian surface. Now, remember, these lines go out to infinity, or rather come in from infinity. Dang, I wish you'd said the other direction. Oh, you did. Whoops. Okay, so there's some radius of our Gaussian surface, and that actually doesn't matter. We're going to get the same answer for the electric field regardless. Wait a second, maybe that's not true. Doesn't the radius of the electric field tell us that, what do you expect? Do you expect a strong electric field near the charge or a strong electric field far from the charge?
Near.
Yeah, so we're going to find that the electric field at this location of the sphere, of the Gaussian surface sphere, is going to depend on the distance that the sphere is away from the center charge. So our integral looks like this. It says, let us integrate around a sphere of the electric field dotted into the area, and we have to do it over the entire surface area of a sphere. Oh boy, that's tricky. Now the reason we chose the symmetry is the electric field here is the same as the electric field here, and there, and there, and there, and there, and there, right? That makes this fantastic. What can we do to the electric field variable if it is constant throughout our integration?
Pull it out.
We can pull it out of that integral. So we get the electric field at each of these locations times, well, oh, we made a simplification because we said electric field is in the same direction as the area. In this case, we'd get a minus sign, right?
Yeah.
Because the electric field is in, but the area is out. That's a little bit annoying, and we'll just be sloppy about it. We'll just say that electric field times the integral over some sphere of the area of the sphere. Well, that simply tells you to find the surface area of a sphere. And you've been taught that, right? Surface of a sphere is what?
4 pi r squared.
Mm-hmm. Now, we know Gauss's law says, let's write down what Gauss's law says. It says take the enclosed charge and divide it by epsilon naught. So I'm just going to write that that's enclosed charge divided by epsilon naught. And then I'm going to say, well, E times the area of a sphere is, look at this, I have this written 3 different times and it's exactly the same thing. But on the next line, I'm going to say the surface area of a sphere is 4 times pi, what else?
R squared.
There's an r squared there. And this is just the charge that's enclosed. Now in this case we can substitute in what we know to be actually the enclosed charge. It's Q1 and it's negative, and then we have to divide by epsilon naught. And if you want to know the electric field at some distance r around a point charge, well, it's just the charge that's inside divided by 4 pi epsilon naught r squared. That's the game. That's it right there. But you remember that 1 over 4 pi kc is epsilon naught, so you can change the location of those two guys. And this is just kc times q divided by r squared. You ever seen that before? I think that you have. You have seen the electric field of a point charge, and that's what it is. Notice this epsilon naught and kc thing, and the 4 pi's jump around all over the place. Cool. Now, I want to do Gauss's law in one more example, and that's the example of these 2 parallel plates. I want to get you a, well, this could be a model of a capacitor for us. So let's draw ourselves another capacitor, and we will set up Gauss's law. And there's another symmetry choice that we make so that the electric field will cancel out in some locations and be awesome in other locations. You guys ready for me? This is the last example. You okay?
Yep.
Everybody all right?
Party on.
Uh-huh. So here we've got electric field pointing the same direction as we had previously, so we need to have some negative charges over here to terminate the electric field, and we need some positive charges over here to begin the electric field. And I need to define something called surface charge density. I'm going to use rho to define that. I'm going to call it surface charge density because, as you guys will see on the first video, the hopefully you have seen it when you're watching this, the surface charge density is the only charge density for a conductor because that's where the charges lie. They lie on the surface of the metal. Surface charge density is sigma, and so my plan is to take a Gaussian surface that looks like this. I want a cylinder. And I want it to go around this plate. Now remember, Gaussian surfaces aren't real, they're a construct of the mind. So I'm going to give you an area A right here and an area A right there. And I'm going to argue that it doesn't actually matter how big the circle is. Do you see why? Let's consider what this flux is. Flux is electric field dotted into area and then added up completely. All of the electric field dotted into the area. Which way is the electric field? Which way is the electric field over here?
There's no electric field.
No electric field at all because the electric field's entirely within the 2 plates of a parallel capacitor. And what about, which way is the electric field over here? Boom. So is any of the electric field leaving the sides of the cylinder?
No.
No. None of the, so there is no flux through the sides of the cylinder. So we could say, let's separate this out into parts. We could call this part 1, and we could call the sides part 2, and we could call the top part 3. So let's see, we've got the sides, and those are flux 2, and that 0 because the electric field is normal to the area. In that case, the area points, let's get some area vectors here. The area is pointing directly out and the electric field is pointing that direction, so it's always going to be normal, so you won't have an electric field there. You won't have a flux, you've got an electric field. And the reason that the flux is 0 over here is because the electric field is in fact 0 outside of the parallel plate capacitor, but surface 3 does have a flux. There is electric field going through there. And we know that the total flux for this Gaussian surface, well, we know that the total flux for the Gaussian surface, which is all phi 3 because those guys are 0, is going to be, what did I say? It's going to be charge enclosed divided by epsilon naught. We also know that it has to be the integral over the area of electric field dotted into area. And the wonderful thing is the electric field, sorry, we need a differential area right there, that's a dA. We know that the electric field is in the same direction as the area is pointing here, so we can simplify that to just E dA, because they're the same direction. We don't have any vector problems anymore. And we're trying to find the electric field. But guess what? Do you think the electric field is the same everywhere on that area?
Yes. Yeah.
In fact, it would be true that the electric field is everywhere the same inside of here. So yes, the electric field throughout that area is the same. And what can we do when there's a constant inside of our integral? Pull that sucker out. So I'm going to say that E times the area of a circle is equal to the enclosed charge divided by epsilon naught. I want to expand this right side though. The enclosed charge has to be the surface charge density times, the enclosed charge has to be the density times what?
Would it be the area?
Yeah, the density times the area of the circle. And then I'm going to divide by epsilon naught. And what about this left side over here? I took out E already, and this says integrate the area differential element over the area, which gives me, you want to guess?
Area.
The area. So this is electric field times area, and this is sigma times area over epsilon naught.
So they cancel out.
They cancel out.
So it doesn't matter the size.
It doesn't matter the size. And we find that the electric field inside of a parallel plate capacitor is simply sigma divided by epsilon naught. Dang. Isn't that beautiful?
Yeah.
Physics. I'll put that here for you. Flower pot. Machine that I've made, it's a few years old, so it's kind of dirty, but I call it my flux catcher. And it is a loop made of metal. Here you can see that it is a fairly continuous loop, and the idea is that if I point it in the right direction, it can catch flux going through it. I'd like you to think of it as if, in this sense, when we get to magnetism, it will be a little bit different, but in this sense, I want you to think of it as a screen that I could wrap around. I could have it flat, or I could wrap it around and form a closed sphere out of this screen flux catcher. So if you have a faucet, let's put a faucet here, we'll put a handle on it and say that out of this faucet is coming some water. And if water is coming out of the faucet, then you could put your catcher, you could wrap it around and make a solid surface. Let's see if I can imagine this. Can you imagine wrapping a mesh bag around the faucet and find that there would be net flux leaving from that faucet? Okay? And you could also say, there's a drain at the bottom of this thing, right? There's a sink here, and help, color for sink. So if the sink is like that and there's a little hole in the sink, flux catcher right here in this stream of water, and if you oriented it so it was like flat like this, by this I mean it's like this direction, like this, then you would catch a lot of flux coming out. In fact, you could even wrap it around the faucet and say that there was flux, positive flux, coming out of the flux catcher. So the word flux comes from the Latin fluxus, meaning flow, and we're going to talk about the idea of electric flux. It does not mean electrons moving from one place to another, but it represents the idea of electric field going through an area. So it's a flowing of electric field more than it is a flowing of electric charge. And I've got this